In this video, we are going to show you how to do a t-test in SPSS. But we're going to start from Excel and import the data into SPSS and go from there. In this VA example data, we have acuities before getting glasses and acuities after getting glasses. And while we're going to do a t-test, paired t-test, comparing before to after on the right eye and before and after on the left eye, if there's no difference, then you should reconsider your occupation of becoming an optometrist. But there's also one other thing we need to point out, a couple things. First of all, if you're going to import an Excel file into SPSS, you must have variable names in the first row and only the first row. And here we have these variable names. I've added some columns here we'll talk about in a second. So it's very important that these columns be uniquely named and that they only fall in the first row and that we have numbers down here. So these are VAs. If we had done 20/80 for 2080, 2080, 2040, that would be a string variable. It would be interpreted as a string by SPSS and no analysis could be done. And that's actually true for SPSS or for Excel as well. If it was 20/80, you can't average that. You can average the fraction, but not the actual expression 20/80. All right, now one common error is for people to just go ahead and take the average of these and compare them in a t-test. That's incorrect because visual acuity is log distributed. So what people do is they take the logmar, compute the logmar. And so we're going to do that in Excel because it's a little bit harder, or it's not really harder, but it's more time consuming to do it using the transform statement in SPSS. So we have, I've already written in these column headings, log, entry, OD, which corresponds to this column, and so forth. So let's see how we do this. So to compute a logmar, we start any formula with an equal sign, and then it's very important to add a minus log, and we're going to do base 10. And so there's 20, 20, 2200, so we need a 20 because when you do the logmar, you do the actual fraction divided by 80. In this case, you would highlight this cell so that we get log 10 of 20 divided by 80. Now you could go through and instead of putting in 80, you could write 80 there and then do every single one of these. So do the next column over with, do that divided by 80 again, 15, 15, 25. That'd take a while. It's much easier to have your formula, use relative information. SPSS or Excel automatically does this by taking this little thing in the lower right hand corner. See that little box there? Our cursor is going to change from a open plus to a little black plus. We're just going to drag it over. And now we have computed the log for each one, and notice it's relatively changed. So on this one, by dragging it over, it knows that the cell it has to divide is 4 over. And of course we can do the same thing by dragging down. Now the other thing we can do is Control C and then coming over here, going down to the bottom, going back up to the top, highlighting this column and hitting a Control V so that we copy all the things over. So again, you can either do that or you can highlight these guys, make that little cross change and go down. It's really your choice as to how to copy the things. Control C and V, Control Copy Paste, Control C V, or drag the little plus. Now we have our data. It's ready. We should save this file in a place where we can easily find it. And let's put it on the desktop and have save data. Now we'll go into SPSS. Then we're going to File, Open, Data. Now here, if we go into the desktop, we've got to go find our stuff. There's the desktop. Notice it only has SPSS files, so we have to come down Files of Type. It's looking for SPSS files. We need to tell it to look for Excel. And here are our Excel files. And here is our VA example data. Now it pops up and it says read variable names from first row of data. Now that's your only choice. If you don't have your data labels in the first row, you would just uncheck this, but then you have to add them later. It's so much easier to have them in your data set. Also note that it asks you which worksheet you want. In this case, there is only data in the first worksheet, so there are no choices, but sometimes you go across various sheets with your data and you got to be sure you import into the right one. So we say okay, and here's our data, a little bit intense on the number of decimal points for the log. Let's go into variable view and let's make this 4 decimal points. See if we can paste that. And then let's make our number of spaces a little bit less, because this basically somewhat controls the width. I'm copying, oops. You know what, sometimes this works and sometimes it doesn't. I'm up to this cell, okay, oh boy, I'm just going to type in 8. Well, that's not going to work either. 8. It's going to be sometimes annoying. Okay, now let's look again. Now you can see we have much more manageable logmar values. So what we need to do, what we're going to do first is just run a paired t-test. And we're going to run a couple of them. And we're going to also compare, and if you were doing a study, you would just do the log values. But because this is an educational video, we're going to see what happens if we do both the logmar and the non-logmar. So paired t-tests are located in Analyze, Compare Means, Paired Sample t-test, and we're going to do Entry, and I'm holding down the Control key, and Exit for the right eye, Entry and Exit for the left eye, Entry, Exit for logmar, Entry, Exit, logmar. So now we're going to do 4 tests. We have some options here. None of them we really care about. Let's say OK. And now you've done 4 t-tests. Pretty easy. Easy peasy. We have the means for each one. we have the correlations. This is a paired t-test, so we can see if the pre and post values are correlated. You can argue whether or not they should be. If people's eyes are pretty bad and they can't get them corrected to 20/20, there will be some significant correlation. I'd like to point out that the left eye was very correlated and the right eye was not. That is likely due to the fact of people consistently doing the right eye first, which is not always measured as accurately, and then the left eye. We're going to get to this logmar and what to do with those means in a minute. Here are the t-tests. So if we look at the entry versus exit on the right eye, this mean is the mean difference. So we look up here, 43.001 is 68 minus 25.7. So there you have it, and this is the standard deviation of the differences. This is the standard error of those differences. This is the t-distribution's confidence interval around the mean. This is the t. The t is the mean divided by the standard error, gives you the t. There were an n of 93. There's one mean, so the degrees of freedom are n minus 1. That's 92. And this was highly significant. So this person can legitimately go on to be an optometrist. We see that all of them were significant regardless of which we do. One thing I'd like to point out is that the VA T for the right eye is 10, but it's 14 for the logmar. And that means if this was a normal distribution, we would call these z-scores. So these are t-scores. But if you think about it, that's the number of standard errors away from the mean, 10, of a null distribution. So the t would be 0 if the null hypothesis were true. This is 10 standard errors away from 0, a null hypothesis of 0. So clearly we reject it. The probability of that is very, very small. Similarly here, you can see they're all looked at as small, but this is the relative difference. So this is 9.8, but with logmar, it's even further out. So the logmar is a more sensitive test. All right, let's do a independent samples t-test. And for this, we're going to look at our 8 variables. We're going to do 8 tests at a time. And our grouping variable is going to be gender. Now this is a string variable, but it lets us do it anyway. And let's hope, I actually forgot to check, that they are all labeled the same. We will see, and notice it, SPSS put quotes around those letters. So we'll see if we get 93. So there does not appear to be any missing data. So fortunately, the person entering this was good, checked the data, made them all labeled the same. If it were me, I would go 0 and 1 and then add the labels 0 equals female, 1 equals male, or vice versa, and have this be a better labeled table than just F and M. All right, so we get the statistics. We get the statistics for each group, the females, for VA at the beginning. And here is the difference. The VA at the beginning, the and the for females, for males, this is the exit VA 26, 23. Looks like the males had a little bit better vision in this first one. And then down here, there's no correlation because the observations aren't paired. There's no way to do a correlation in this one. But we want to make sure you don't get confused. This significance is not the significance of the t-test. This is the significance of Levene's test for equal variances. And I forgot to do the normal testing, the normal assumptions. We'll do that when we're done here. But basically, if we look at this, let's just come up here, and this is evaluating the entrance variables. So we don't compare pre and post. Here we're just looking at the pre and if there's a difference in males and females. And we're not just looking at the difference of means, but Levene's test says, is there a difference in variance? And you can see there's 44 versus 22. That looks pretty different. And in fact, Levene's test, which is we square this, the larger standard deviation divided by the smaller square of the standard deviation, in other words, the variance. We look at the variances, the ratio of the variance, it's distributed as F, and we reject it with that P.01. Now, also like to point out, it's rejected here on the right eye for the Snellen test. It's also rejected at using the logmar. So the logmar doesn't completely correct that. It does on the left eye. And then the and now this T is in fact the T that is come from, remember that the T equation is the mean of one minus the mean of the other divided by the standard error of the differences. So here is the mean difference, which is 19.21, which is 72 minus 53. The standard error of the difference is the square root of the sum of the squared standard errors. Here's the confidence interval of the difference. Notice minus and plus overlap 0, so we cannot reject the null hypothesis. And we see that that's greater than 0.05. Now, because this was significant, there's two ways that we can look at the t-test. One is equal variances assumed, and one is equal variances not assumed. Because we reject the null hypothesis, we cannot assume that the variances are equal. So we use this second row. And what's different is that the degrees of freedom have been adjusted downwards by something called a Satterthwaite adjustment. And thus it's now significant that unequal variance and the adjustment has made this a significant difference. And it's the confidence interval of the difference is 4.7 versus 33. So the reason this first one wasn't significant was because the variances were so different. But if you take into account the difference in variances, you actually find that this was significantly different. Let's look at the corresponding logmar. Entrance VA. Now this one wasn't quite so generous at the second one. We did not meet the criteria of 0.05, though, you know, it's in the neighborhood. If you tried to say that was close to significance, some people would say, hey, it didn't meet 0.05, whereas others would say, you know, it's okay to say it's in the neighborhood. I say it's okay to say it's in the neighborhood, but it is not significant. Now, if you had a whole bunch of measures and one was 0.06 and all the others weren't in the neighborhood of significance, I would say you would want to ignore that. So that's how you do a t-test, paired and independent. Now, when you're writing stuff up, you want to make graphs and do all sorts of pretty things. And so what I would suggest that you do is, now, here's the thing. It's kind of, if you're going to report a paired samples t-test, the data is based, the significance is based on the differences. So these are the data that you're most interested in. I'm going to copy this. I'm going to go to my Excel spreadsheet. Oh, I don't have example data opened up. Well, we'll go to here. So, and then I'm going to copy it and paste it. Oh, notice when I paste this second one. I could paste the first one. And notice how this has lines, but to be honest, sometimes these lines and the collapse merging of the cells gets in the way, and it's pretty annoying. So I usually do it without having the formal chart in there. All right. The other thing, let's see. Let's bring in the independent one. Now in the independent one, in fact, you're comparing different means. So it is okay to talk about the independent means. Although if you're going to report something in your text, you would probably want to report the confidence interval of the difference. But if you're making a plot, you would probably want to plot the statistics. So let's copy that and put that in here. Now, we have found that and notice this says 0. When you get something like that, we would say p less than 0.001. We wouldn't say that p is 0. P is less than 0.01. But what we want to do is compute effect sizes. Now the effect size for a paired t-test is the difference, whoops, put in an equal sign, the difference divided by, is it the standard deviation or the standard error? Effect size is based on the standard deviation. So we would go to there, and there is our effect size. And notice that the logmars are about 50% greater. For the independent t-test, we have copied in our data. We're going to look at equals mean of one minus the mean of the other divided by the average standard deviation. Although this is somewhat questionable in this case because the standard deviations are not in fact equal. So we might be better off doing the standard deviation from the standard error of the differences for the denominator of the t-test. But anyway, here we have, now this one you can't just drag it down because it does too many. I mean, you could and then delete, or you can just copy from the beginning. And here we can see effect sizes. notice there was reasonable effect size difference at the entry, but not so much at exit. Entry, not so much at exit. Remember, our effect size criteria is less than or greater than 0.5 is kind of our rule of thumb. Up here, these are all big differences. All right, so that is the t-test and computing effect sizes. Now, I had forgotten to test the assumption of normality. So let's go back and do that. And the way we do that is to go into Analyze, Descriptive, QQ plots, and then we're going to come down here, bring in our variables. The test distribution is normal. We say OK. And whoa, that is the VA, the Snellen VA. We want this to be a straight line. That does not look very straight. Here's the left eye, the exit right eye, the exit left eye, and here's the logmar. Do you see why we want to use logmar? Look at that. Amazing. Pretty straight. A little off at the end, but pretty straight. Pretty doggone straight. So we meet the assumption, for the most part, of the normal distribution. We're using logmar, but not Snellen. We do not always meet the equal variances when we look at the before and after of the here's our actually we didn't really test equal assumptions. It's not really, we can look at that difference, but we didn't do that. We just came in. We see here that for our Snellen test, let's actually go down to logmar because that's what we want to use. We can see that for some equal variances, and a lot of times people say if it's not greater than 0.1, you should go and do it. So for example, that's okay, not okay, okay, okay. And so you would use the equal variances not assumed. We'll talk later about nonparametrics on another point. One final thing, this video is running a little long, but we have logmar values. Now, so our means are this. Really, you can keep it that way, but a lot of people would be interested in the original. They're just more comfortable with the 2020 kind of notion. So we can convert them back by going equals. It's a base 10 log, so we go equal 10, excuse me, it is minus, don't forget that minus sign, 10 to the mean. Okay. Don't forget the minus sign, just put it in the right place. So it's equal 10 to the minus logmar value. And you can copy, oh no we can't. Okay, so down here, oh, we don't do it there. Down here, you go equals 10 to the minus, nope, 10 raised, The little caret is the exponential minus that. And we go down there. Now this is the fraction. This is the 20 divided by something. So if you have a fraction, you want to get the denominator, and it's 20 over something. We would divide 20 by the fraction, and we get the denominator. And if you wanted to, you could reduce the number of decimals up here. Click, 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 click. And so that's 20, the mean is 2062 compared to 2072, 2049 compared to 53, and so forth. The numbers are slightly different when you get this. And these are called geometric means because they've been logged and then converted back. So you would refer to a converted logmar as a geometric mean. All right, that's it.